Now let's come to the main attraction, right, which is while loops, right. So what to do about while loops? Okay. So how to determine, right, that Hoare triple involving a while loop is valid or not? So for that, our strategy, right, is to use loop invariants, right. So this is our goal, right. So we want to prove validity of Hoare triples like this, right, where my program contains a while loop, right. So I have this program which contains while g do c, and I want to show that this particular Hoare triple is valid. Okay. So this is our goal, and we want to use loop invariants for this purpose. So we have seen that both SP and WP require non-terminating procedures. So we will use a loop invariant I intuitively, right. This loop invariant I is an over approximation of the states which are possible at the beginning of any iteration of the loop. Okay. So we assume that I will be provided by the programmer, right. So I will be part of the program itself. So in fact, what we will do is we are going to change the syntax of imp, right. So for any while loop, the programmer also needs to provide the loop invariant, right. So this is given by this particular new syntax, right, which is @I. So whenever you see @I, so any while loop has to include this @I, and this I is assumed to be a formula, right. So this is another first order logic formula, but is also the loop invariant. And once you have such a program which is annotated with loop invariants, Hoare logic is going to provide inference rules in order to prove that I is indeed a loop invariant, right? And in fact, to show that this particular Hoare triple is valid. Okay. So let's go step by step now, right? Let's first try to understand what is this loop invariant I, right? So if you consider a while loop, right? This is the flow chart of a while loop, right? So this P is the precondition, right? So these are the set of states which we are beginning the while loop from. Right. So my while loop, what is it going to do? So it's first going to evaluate, right, this loop conditional which is G. So for all states which satisfy G, you are going to execute C on them, and then you are going to return back, right, to this conditional. And for states which don't satisfy G, you are going to exit out of the loop. And when you exit out of the loop, you want to show that the post condition Q holds. So in this picture, right, where does I stand, right? So I is used in order to depict the set of program states which are at the beginning of any iteration of the loop, right. So let's consider any iteration of the loop, right. So if you consider the 0th iteration, right, this is the very beginning, right. So these are essentially all program states which are in P, right. And in addition, right, any state which occurs after any number of iterations, right. So let's say after you do one iteration, right, which means after you execute C once, right, you are again going to get a new set of program states, right. So those program states will also be encapsulated by I. So I essentially encapsulates all those program states which are reachable at the beginning of any iteration of the loop, right, including the very first iteration, right. So that's what we want. So that's what I is going to encode, right, and we assume that I is going to be provided by the programmer. So what are some properties that I needs to satisfy, right? So in order to know, right, that I actually encodes all the program states which are reachable at the start of any iteration of the loop, we need I to satisfy three properties, right, which are that I must hold initially at the start of the loop. So when you begin the execution of the loop, right, so this is the 0th iteration, or rather the first iteration, right. So at the beginning, at the start of the first iteration, all the program states P, right, are going to flow, right, into I, right. So I must hold initially at the start of the loop. Furthermore, I must also hold at the end of every iteration of the loop, right. So if you look at what happens, right, once an iteration finishes, right, once you execute the body of the loop, all those states come back, right, and then you will again apply the loop condition on them, right. So which means that all states which can occur at the end of any iteration of the loop must also be encapsulated by I, right, because the states which occur at the end of any iteration, those are the exact states which will occur at the beginning of the next iteration, right. So if you take the first iteration, right, the states which occur at the end of the first iteration, all of them will appear at the beginning of the second iteration, right. And in general, any state which appears at the end of the nth iteration, it will appear at the beginning of the n plus 1th iteration, right. So therefore I must hold at the end of every iteration of the loop, right, because we want I to encode all program states which are possible at the beginning of any iteration of the loop. Okay. Now finally, remember that our goal is to prove a Hoare triple is valid, right? So I must be good enough to prove that the Hoare triple is valid, right? Which means that after you exit the loop, so if you consider all the program states which exit the loop, right, then those program states, right, must satisfy the post condition, right, which is Q. So which means that I must encapsulate those program states, right, which imply the post condition. Okay. So these are the three properties that if I satisfies, then I will be a loop invariant, and if I is a loop invariant, then you can use it to prove the validity of the Hoare triple. Okay. So let us see, right, how we can now come up with an inference rule, right, for proving validity of Hoare triples involving while loops, okay, but using the loop invariant I. So let us first look at an example, right, of a loop invariant. So let us consider this piece of code, right. So here I have a while loop, okay, which is this one. I haven't specified a post condition here, right. So what is this program doing? So it starts in a program state where the value of n is greater than 0. So this is the precondition. This is P, right, assigns I equal to 0, j equal to 0, and then there is this while loop, right, which essentially counts up to n, right. So while I is less than n, it does I equal to I plus 1 and j equal to I plus j, right. So this is the body of the loop, okay, this is C. Now let us try to come up with some loop invariants for this particular loop, okay. So remember that loop invariant should satisfy three properties, right. So here we don't have to worry about post condition because there is no post condition, right. But any loop invariant that we come up for this loop, right, it should hold at the beginning of any iteration of the loop, okay. So let's look at some candidate loop invariants, okay. Let's look at the first one, right. So I is less than or equal to n. So is this a loop invariant or not? Okay. So in order to kind of reason about this, right, you need to see whether or not this holds at the beginning of any iteration of the loop, right. So let's consider the first iteration. So when you're just starting the loop, right, at that point the value of I is 0 and the value of n we know is greater than 0, right? So this is given by the precondition, right. So then clearly it holds at the beginning, okay. Does it hold at the end of every iteration of the loop, right? So we know that this loop is going to execute only if the value of I is less than n. So if I is less than n and you do I equal to I plus 1, remember that I initially was 0, right. So if you do I equal to I plus 1 and you know that I is less than n, after executing the body of the loop, you are guaranteed that the value of I is going to be less than or equal to n, right, because since I is less than n, right, at max I can be less than or equal to n minus 1, right, because I is strictly less than n, and if you do I equal to I plus 1, that means that I will be less than or equal to n, right. So remember that any state which will occur at the end of any iteration of the loop, it's also going to come back to the beginning of the next iteration, right. So we need to consider states which can occur at the end of the iteration of the loop as well, of any iteration of the loop. So in any iteration of the loop, when you begin it, you know that I is less than n, right, because this conditional only allows those states where the value of I is less than n, and if you execute the loop body, I can be incremented by at most 1, so therefore I will be less than or equal to n, right. So therefore, right, this essentially shows that at the end, at the beginning of any iteration of the loop, the value of I will be less than or equal to n, right. So therefore this is a loop invariant. Now through a similar reasoning, right, you should be able to see, right, that I is less than n, this one is it a loop invariant or not, right. So this one is actually not a loop invariant, right, because as we have seen, right, suppose we take I equal to n minus 1, right. So this is a value which is less than n. If you execute the body of the loop, right, then after executing the body of the loop I will get I equal to n, right, which will occur then at the beginning of the next iteration, right. But we know that loop invariant should encapsulate all states which occur at the beginning of any iteration, right. So therefore I is less than n is not a loop invariant. Okay. So what about I is greater than or equal to 0? So again that is a loop invariant, right, because I is always incremented by 1, right. So if you start the loop, so at the beginning of course I is equal to 0, so it clearly satisfies I is greater than or equal to 0, and if you execute the loop, right, it's only going to increase the value of I by 1, right. So I will remain greater than or equal to 0, right. So the first and the third are loop invariants, the second is not a loop invariant. So let's look at the inference rule now for while loops, right, which uses the loop invariant. Okay. So again this is following the same format, right. So I have my conclusion, I have my premise. Let's look at the conclusion first, right. So the conclusion says that if you have a while loop of this form, right, while f at the rate I do c, notice that I is already annotated, right, as part of the program, then you can deduce this particular loop invariant, or rather you can deduce this Hoare triple. So this Hoare triple says that the precondition is I and the post condition is I and not of f, right, where f is the loop conditional, right. So you can deduce this Hoare triple, but as a premise you need to deduce another Hoare triple, right, which is I and f ci. Okay. So intuitively, right, what does this mean? So it means that if you start the while loop in a state which is in I, right, if you enter the body of the loop, right, which is C, so you can enter the body of the loop only if f holds, right. So now my premise says that if you start in a state where I and f hold, and if you execute the body of the loop, you are guaranteed to end up in a state in I, right. So this means that I does encapsulate all the states which will appear at the end of any iteration of the loop, and all those states will then transfer to the beginning of the next iteration, right. So therefore indeed I is indeed a loop invariant, right. So if you start the loop in a state which satisfies I, then my premise is going to guarantee that you are never going to leave this state, this set of states I, so you are always going to remain in the set of states I, right? And finally when you exit the loop, right, so you will exit the loop when the loop condition is not satisfied, right. So all those states which will exit the loop will satisfy I and negation of f, right. So I know that so all the states which can appear at the beginning of any iteration of the loop is I, and out of all of those states, right, I will just exit with all those states which satisfy negation of f, right, because they will be the states that will exit out the loop, right. So that's why this Hoare triple, right, the conclusion is also valid. Okay. So this is following the semantics of while loop, right, that we have seen. Okay. And this is how you can use the annotated loop invariant in order to deduce a Hoare triple, right. So one thing that you should notice, right, is that in the conclusion I have a while loop, but in the premise I don't have that while loop, right. So in fact this is how we have kind of gotten rid of that while loop, right. So in order to deduce the conclusion I will need to prove the premise, but the premise itself only contains the body of the loop, right. So for the body of the loop I can use the other inference rules, right. So I can use, for example, sequential composition, if then else, right, assignment statements, assert, assume, and so on. Okay. Of course, I mean there may be nested loops, but in that case again I can use the same inference rule, right, for while loop. Okay. So this is R while 1. So you can imagine that there is going to be another inference rule, right, so which is R while 2. So let's look at that inference rule. So in R while 1, the precondition and the post condition were based on I, right, in the conclusion, where I is the loop invariant. But in R while 2, my precondition and post condition are arbitrary, right. So if I want to prove an arbitrary Hoare triple, right, or if I want to show that this arbitrary Hoare triple P while f at the rate I do c, Q is valid, again I can use the loop invariant I, right. But in addition to this particular Hoare triple, right, which is kind of the same as the Hoare triple in R while 1, I also need to prove that these two formulas are valid, right. So the first formula says that P implies I, right, which means that if you start in a state which satisfies P, right, then it should also satisfy I, right. So this is corresponding to the fact that at the beginning of the while loop, right, at the beginning of the first iteration, my set of states should be encoded, right, by I. So I should encompass all states which are possible at the beginning of any iteration of the loop, and particularly at the beginning of the first iteration of the loop as well, right. So, if P implies I holds, then indeed it is the case that I will encompass the states which are possible at the beginning of the first iteration, right. So, I and F C I we have already seen that this Hoare triple guarantees that if you execute C, the body of the loop, right, in a state which satisfies I and F, you will end up in a state which is in I, right. So, you will never leave the set of states I after any number of iterations of the loop, right. And the last formula, right, this is I and not F implies Q. So, here my post condition is Q, right. So, essentially I am doing kind of post condition weakening here, right. So, if I and not of F, right, which is what I can deduce using R while 1, if it implies Q, then I can also deduce this Hoare triple, right, which where the post condition is Q itself. Okay. So, in a sense, right, R while 2 is using both precondition strengthening and post condition weakening, right, on R while 1, right. So, both of these together, right, will give you R while 2. Okay. So, again let us look at an example, right. So, suppose we want to prove that this particular Hoare triple is valid. Okay. So, here my precondition is I is equal to 0 and n is greater than 0. My while loop is simply, so my program is a simple while loop, right, it just increments I by 1 in every iteration, right, until I is less than n, right. So, while I is less than n, and my post condition is I equal to n. Okay. So, now of course, I mean one thing is missing in this program, right, which is the loop invariant. So, you cannot prove a Hoare triple like this, right. So, because we will assume, right, that all the while loops are annotated with loop invariants. Okay. So, first we need to find an appropriate loop invariant for this particular while loop, which can help us to discharge this particular post condition. Okay. So, what are different loop invariants? In fact, there are many loop invariants for this particular while loop, right. So, I is greater than or equal to 0, this is a loop invariant. I is less than or equal to n is also a loop invariant. N is greater than 0 is a loop invariant, and so on. Okay. But which loop invariant to use, right? So, if I use, for example, I is greater than or equal to 0 or n is greater than 0, I can use those, right, but I won't be able to show this particular post condition, right. So, in order to show this post condition, I will have to use this loop invariant, okay, which is I is less than or equal to n. Okay. So, we will take I, right, this capital I to be this loop invariant, I is less than or equal to n. So, once we have that loop invariant, I can then simply plug in, right, the inference rule. So, I can plug in the different components, right, of the inference rule for while loops. Okay. So, this is my Hoare triple that I want to prove, right. This is exactly the same as what I have here, except that I have added this loop invariant, right, which is I is less than or equal to n. Okay. Again, this is purely syntactic now, right. So, in order to use the inference rule for while loop, I just need to plug in the appropriate components, right. So, this is P, right, this is I, this is Q. So, I have 3 components, right. One is, the first component is P should imply I, right. So, I is equal to 0 and n is greater than 0 should imply I is less than or equal to n, right. So, this is P implies I. The second is I and F C I should be a valid Hoare triple, right. So, I is less than or equal to n, F, right, this is F. So, this is I is less than n. The body of the loop, which is I colon equal to I plus 1, should imply I, right, which is I is less than or equal to n. And the third is I and not F should imply Q, right. So, I is less than or equal to n and not F, right, which is I is greater than or equal to n, should imply I equal to n. Okay. So, first notice that both, let us look at both these formulas, right. So, I equal to 0 and n is greater than 0, does it imply that I is less than or equal to n? So, in fact, it does imply that, right. So, this formula is valid. Similarly, I is less than or equal to n and I is greater than or equal to n, this implies that I is equal to n, right. So, this formula is also valid. So, both this, right, you can simply give these 2 formulas to any SAT solver, right, and they will say that both these formulas are valid. Okay. So, now the only thing that is left is to show the validity of this Hoare triple, right? And here again I can use the assignment rule, right? So the assignment rule says that wherever I see I, substitute with I plus 1, right? So in the post condition, right, I will get I plus 1 is less than or equal to n, which is the same as I is less than or equal to n minus 1, right, which is the same as I is less than n. And indeed that is exactly the precondition, right. So the precondition I is less than or equal to n and I is less than n, this is equivalent to I is less than n. So simply by using the R assign rule, I can deduce that this Hoare triple is also valid. I don't need to prove anything else. So that's it. I'm done. Okay. So I is less than or equal to n and I is less than n implies that I is less than n. Okay. So there is one important distinction, right, between loop invariants and inductive loop invariants, right. So what we have seen so far, right, are what are known as inductive loop invariants, but a loop invariant is a more generic thing, right. So let's kind of try to understand this distinction between loop invariants and inductive loop invariants. So let's consider again this same piece of code, right, that we had seen earlier, right. So let's look at this j is greater than or equal to 0. So is this a loop invariant or not for this particular code? So in order to find out whether j is greater than or equal to 0 is a loop invariant, you need to see that this holds at the beginning of any iteration of the loop. So at the beginning of the first iteration, the value of j is equal to 0, right, so which is greater than or equal to 0, so it holds. Now in every body, right, rather in every iteration, right, what you are doing is you are adding something to j, right, so j is equal to I plus j. Furthermore, what is it that you are adding, right? So you are adding this value I, but I also know that I itself is also a positive number, right, because it starts with 0 and in every iteration I am simply incrementing the value of I, right. So this means that I am essentially adding a positive number, right, to j in every iteration. So if I start with a value of j which is greater than or equal to 0, in every iteration of the loop body, right, or in every iteration of the loop, I am simply adding more things to j, right. So therefore j is greater than or equal to 0 is clearly a loop invariant. So it holds at the beginning of the loop and it also holds at the end of any iteration of the loop, right, which means it holds the beginning of the next iteration of the loop. Okay. So it holds at the beginning and at the end of every iteration. However, this j is greater than or equal to 0, right, this is not an inductive loop invariant. So in particular, right, let's look at what the strategy that we have seen, right, the inference rules that we have seen for the while loop, right. So if you, for example, annotate this, right, with let's say j is greater than or equal to 0. Okay. Now if you want to show, right, that this is a Hoare triple, this is rather a loop invariant, you will need to show, right, that this I and f c I, this is a valid Hoare triple. So I will be j is greater than or equal to 0, f will be I is less than n, c is the body of the loop and j is greater than or equal to 0, right. So we will need to show that this particular Hoare triple is valid, it is the same as this Hoare triple. So only if this Hoare triple is valid, then I can use I as a loop invariant in my inference rules, right. So recall that the inference rules that we have seen for while loop, right, both those inference rules have this particular Hoare triple in the premise, right. So if I can show, only if I can show the validity of this Hoare triple, can I use I, which is this j is greater than or equal to 0 as a loop invariant, right. But in fact, does this particular Hoare triple hold or not, right. So we can again, right, propagate this backwards, right. So j is greater than or equal to 0, let's propagate it backwards, right. So using R assign and R seek, right, I am not going to go through all the calculation, right, you can do it yourself, but eventually, right, you will end up with this I plus 1 plus j is greater than or equal to 0. Okay. Now does j is greater than or equal to 0 and I is less than n, does this imply I plus 1 plus j is greater than or equal to 0 or not, right. So in particular here my precondition, right, is only saying that I is less than n, but I don't know what is n, right. So n in general could be a negative number, right, because this particular precondition itself doesn't constrain the value of n, right. So it just says that I is less than n. Okay. So using simply this particular precondition, I cannot show that this precondition holds, right, because I could be a negative number, right, could be a very large negative number, in which case I plus 1 plus j need not be greater than or equal to 0, right. So therefore you cannot use R strengthened pre, right, because the original precondition, right, which is this precondition that we want to show, this doesn't imply the precondition that you get by using R assign and R seek, right. So in fact you cannot use our existing inference rules in order to show that this Hoare triple is valid, and in fact this Hoare triple is not valid, right. So this Hoare triple doesn't hold. I can find a value of I, j and n such that it will satisfy this particular formula, but after executing this it won't satisfy j is greater than or equal to 0, right, because I can always assign a large negative value to I, right, in which case this j colon equal to I plus j, this will not ensure, right, that j will be greater than or equal to 0. Okay. So in fact j is greater than or equal to 0 is not an inductive loop invariant, right. So the thing to note here is that the inference rules for while loop, they only allow inductive loop invariants, right, they don't allow arbitrary loop invariant. So even though we know that j is greater than or equal to 0 is a loop invariant, you cannot use it in the inference rules for while loops, right, for Hoare logic, because it only allows inductive loop invariant. So you need to make sure that the loop invariant is inductive, which means that this Hoare triple should hold, right, the I and f Ci, that Hoare triple should hold. So in fact in this case I can strengthen my loop invariant, right. So I can, instead of taking just j is greater than or equal to 0, I can take this as a loop invariant, right, j is greater than or equal to 0 and I is greater than or equal to 0, and in fact this is an inductive loop invariant, right, in the sense that if you execute the body of the loop, right, beginning from any state where this formula holds, right, j is greater than or equal to 0 and I is greater than or equal to 0, then on executing the body of the loop you are guaranteed to end up in a state where it continues to hold, right. So because you are only adding things, right, to I and j. Okay. So this is an inductive loop invariant and this can be used in the inference rules, right, for the while loop. Okay. So and you can use that to prove other post conditions. Okay. Okay. So we will end here now, we will continue with this in the next lecture. Okay. Thank you.